T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And ignition of the Taurus rocket with glory, monitoring how changes in Earth climate may affect our lives.
We are at T plus 300 seconds. The vehicle speed error is indicating underperformance, which is expected due to a fairing not separating.
Originally taking flight in the 90s, NASA's Taurus series rockets were designed to carry satellites into orbit. That video was taken in 2011, when for a second time in 2 years, a Taurus rocket failed to reach orbit. Although the failure might not look catastrophic in the video since there's no fiery explosion like the Challenger, the back-to-back failures resulted in a loss of $700 million for NASA. So what caused this series of failures? Well, as stated at the end of the video, the failure was suspected to be caused by a fairing not fully separating. The T8 and T9 rockets, the two failures in question, both used frangible joints to separate the payload from the rocket. Frangible joints are three plates joined by bolts. In the middle of the joint, the inner plate is cut off and the two outside plates wrap around a large cavity. In this cavity, there is a material with an explosive on the inside. The material is designed to expand when the explosive goes off, fracturing the narrow points on the two plates surrounding the cavity and causing stages of the rocket to separate. The materials making up the two external plates have to meet very high standards. NASA must ensure they can withstand the conditions of a rocket launch and keep an 80-ton rocket held together, but also be brittle enough to be fractured by the expansion of the material inside. In the T8 and T9 rockets, it was found that these plates failed to fracture, keeping stages of the rocket held together and not shedding enough weight to reach orbit. The remainder of the rockets was either burnt up in Earth's atmosphere or scattered throughout the Pacific. The NASA investigative team determined 3 different factors all related to frangible joints that caused the rocket to fail. The first reason given by NASA is that what NASA refers to as the charge holder, which is the material that houses the explosive, contracted due to the temperature in the atmosphere. NASA says these charge holders experienced a 0.38-inch contraction. The second reason given by NASA is that the ligament, which is the narrow part of a frangible joint meant to fracture, grew by between 0.003 and 0.004 inches between the time it was extruded and the time it was used. NASA claims that the die used to make the extrusions caused the extrusions to wear asymmetrically over time. However, measurements taken by NASA from 2002 to 2007 showed that the extrusions were still within the proper dimensions, although NASA claims they would have been on the high side. NASA also claims that these two factors contributed to the failure, but they alone were not the cause of the failure. In a public investigative summary released by NASA in 2019, NASA gives the material requirements for the two plates. The plates were to be made of 6061 T6 aluminum and are in accordance with the Aero Metals Alliance's QQ8 200/8 T6511 alloy. NASA required a minimum yield strength of 350,000 psi, a minimum ultimate tensile strength of 380,000 psi, and a minimum elongation of 8%. These values are comparable to some steels, maintaining the advantage of aluminum's weight. The investigative team at NASA found that the plates used, which were created by a third-party company, SAPA Profiles Incorporated, or SPI, did not meet the minimum requirements given by NASA, and that the data given to NASA was forged. While we have no way to know what the properties of the actual material used was like, we can talk about why the material NASA requested required these specific properties. T6511, which is a 6061 aluminum alloy, or T6511 is the method of heat treatment used, provides one of the highest ultimate tensile strength and yield strength you can find on aluminum alloys. Yield strength is defined as the maximum stress that can be applied to a material before plastic deformation occurs. Ultimate tensile strength is defined as a material's maximum resistance to fracture. So it is the point before fracture at which a material can withstand the highest stress. Although it may sound weird for NASA to define the minimum values of properties for a material they want to fracture, when these two values are high, brittleness is also very high. meaning that the shock from an explosion or the rapid expansion of an object against the material will cause it to shatter. 6061 is an aluminum alloy containing magnesium and silicon as its two biggest alloying elements, along with iron and copper following shortly after. Magnesium increases the weldability of a material and increases corrosion resistance. Silicon reduces melting temperature and improves fluidity, improving the weldability. Iron serves to increase yield strength but reduces elongation. And unlike with steel, copper actually increases the strength and reduces ductility. Its alloying elements provide many desirable factors for use in a frangible joint. According to Aero Metals Alliance, T6511 is created when the alloy is solution heat treated and stress relieved by stretching, then artificially aged with minor straightening after aging. T6511 is a more specific version of the T6 temper type, which is the same method without the straightening or stretching. Solution heat treating involves bringing a material to a temperature where the alloying elements are dissolved in a solid solution in the aluminum and held for a specific amount of time. In the case of T6511, there are a few different methods, but the graph I have shows heating the material to 535 Celsius for 2 hours. This will cause the alloying elements, mainly magnesium silicide, to be dissolved into the aluminum, strengthening it. After this step, the material is quenched, which involves the rapid cooling of a material in a solution. When quenching is performed on 6061, it traps the magnesium silicide inside, preventing it from precipitating. With quenching, the faster the material cools, the less the alloying element will precipitate. But this also creates a lot of internal stress. We want to minimize the amount of material that precipitates, but also don't want to deal with this stress. So different methods are used to reduce this stress, most commonly tempering. In the case of T6511, however, stretching is performed. When aluminum is stretched, it is usually performed in a roller, which elongates grain boundaries, pushing atoms further apart and relieving internal stress. Next, aging is performed. When aged, the dissolved element forms in uniform arrays that increase the hardness of a material, but it reduces the ductility. For T6511, there are a variety of times and temperatures that aging can be performed at, but the graph I have shows at 158 Celsius for 10 hours, and it is recommended to just air quench your material afterwards. All of this results in a form of 6061 with a very high strength and a low ductility. However, this much heat treating can often result in a material that is very warped, so for T6511, straightening is performed. When straightening aluminum, it seems that there are a variety of ways to go about it. However, most methods use a large machine called a straightener. The final result is perfect for a frangible joint. Again, it is not publicly known what the actual properties of the material used in the rockets were, but the underperformance was likely the result of improper heat treatment. This case goes to show how large the effect is that using slightly different materials for a small part of a project can have on the entire thing. Hundreds of millions of dollars and years of research were poured into these missions, just to be thwarted by a company who gave NASA a faulty material and fraudulent results. Overall, the NASA investigative team found that SPI's fraudulent test results affected over 250 customers. The company has since been fined about $47 million, which has been distributed to the victims. And finally, after the failure in 2011, Taurus was renamed to Minotaur C, and on Halloween Day of 2017, a Minotaur C rocket successfully carried its payload into orbit.
Castor 120 Stage 0 motor propels the 104-foot tall Minotaur C vehicle away from Vandenberg Air Force Base. Stage 0 motor pressure is nominal. Attitude remains nominal. And we have lost telemetry in the center.
And this is the rock.
This is vehicle on countdown 1. We have recovered telemetry in the center. We are now 230 seconds into the flight. Attitude remains nominal, and we're in stage 2 burn. Stage 2 burnout. Vehicle energy state is good. Fairing has separated. I repeat, the fairing is confirmed to have separated and fully deployed.